Thank you very much for having me. It's kind of amazing to come here. Thank you for Deliveroo. Yeah, amazing venue, and there are so many people here. It's kind of insane. It's been a long time since I've actually done a talk at the Go meetup. I think it might be in a couple of years. So yeah, it's kind of amazing to see what's happened with so much hard work. Thank you. Anyway, yeah, I'm going to talk a bit about context with this truly awful title, so apologies for that. In true Monzo style, this is maybe a better title for my talk, and I'll come back to that in a minute. So yeah, quickly, I'm Matt. I am a backend engineer. If you want to ask me any questions after, I'm here on Twitter. Otherwise, I'll be around all evening. So yeah, if you want to nerd out about banks and financial systems and other things like that, come find me. And yeah, I work at a bank. Thankfully, not a bank like this. But I really didn't think I would work at a bank at any point in my career. I used to do nice websites and things like that, and love CSS. And then I got drawn into the dark side of back-end engineering, and somehow ended up working on financial systems, which is really not what I expected. So yeah, I work at Monzo. For anyone who's not heard of Monzo, we are a bank. We kind of are trying to change the way that people interact with finance. So rather than the kind of terrible horror stories you have, basically everybody has from every bank, every single person. Every bank that I've banked with has kind of charged me horrible amounts of fees and really taken advantage of me. And I'm reasonably well off and fairly privileged. So that's not the case for a lot of people. And we're kind of trying to change that at Monzo. So although there were the kind of whizzy technical features that we have, our company is really about kind of enhancing access to finances and kind of the way that the things basically people need to live these days. Anyway, fancy app. You can use if this then that to do stuff. You can do things like splitting your bill. You can get receipts, itemized receipts now with Flux. So you can see that you bought too many granola berries. And you can do cash ISAs and stuff. But my favorite feature is still real-time emojis to your phone. In this case, 2 emojis, a burger and a bear, if you go to Burger Bear, which is just up by Old Street. And the amount of code that delivers sweet emoji to your phone in real time is a little bit excessive. But hey-ho. So a long time ago, 2015, we thought that we would launch a prepaid card. And that was really 50-50. We didn't think anyone would want one, to be honest. It wasn't very good. So we had 3,000 made, and we basically forced people to have them who we knew, and they were quite reluctant. And sometime later, we released a beta thing, and we gave people a better app and a better experience, and then we kind of became a bank and added proper banking features, at which point things kind of rapidly spiraled out of control. So at the moment, we're the fastest growing UK bank. We have 1.8 million customers, adding about 35,000 a week. But all of that kind of begs the question, why am I here talking to you about contexts? So who's heard of context package? Everyone, amazing. So the context package is one of these really kind of small things in the Go language that people don't pay a huge amount of attention to. And I find it really interesting because it serves so many different use cases, and lots of the functions throughout the standard library have now started integrating context, so it's kind of becoming the default case. But lots of code that I interact with still doesn't provide me the mechanism to use it with a context. And for me, that's quite interesting because they're extremely powerful, but I feel often kind of maybe slightly misunderstood. So there's lots of stuff that they can do, but I think a simpler way to think of them is something like this. It's like a sweet purse that you can put stuff in, and sometime later, you can take stuff back out of it. And it has loads of other functionality that's really useful, but if it's a really a simple way of thinking about it, you have something that you can carry around with you. That's it. And everything else is built off that extremely simple kind of concept. So a context has an interface like this, which is very dense and kind of intimidating, to be honest. There's a lot of stuff going on in 4 lines of code there. But the functionality we have is top one. We can set a deadline. So that means when we are creating this object, we can say, hey, at some point in the future, at this time, like, consider yourself finished. And if we set that, when that time elapses, this channel will close. And that means that we can do quite interesting things off the back of that, which I'll come on to in a minute. So those two little things mean that you can pass this thing around, and you can pass it through your code, even though you don't have to pass like an actual variable that is, hey, please stop doing this thing in like 5 minutes time. And so by being able to put that thing in, or putting other variables essentially in your sweet purse that you can carry around, you don't have to have like a million parameters in every single function call if you need to use those things or like recover them sometime later, including if you've gone through like a load of third-party libraries that don't support those kind of parameters that you need. So the other thing you can get is when something has happened, when the context expires or something like that, you can get an error back out. And crucially, you can store values in this thing. So you can store a value with which has a type of interface. I think some people will see the problems that are about to happen here. And you can get it back out as an interface, which again, just throws all your type safety away. However, the flexibility of that means that you can pass anything around, for better or worse. And if you keep things nice and simple, for better. If you choose to pass pointers around, which I would not recommend, for worse, which we'll come on to in a minute. So in the case of a context, generally when you are starting your code, you create what's called a background. And this is like the beginning of everything happening. Every function call from that will be like a descendant of this main background context. If you want to store a value, you can use this withValue function. So what you're doing here is you're giving this function on the package level the context that you just created, and you're saying store this key, say trace ID, with a value of boop. And that is not going to mutate the context. It's going to give you a new context back. And then if you use the value here, I've trimmed this for brevity, but we'll come on to that in a minute. If you grab the key by trace ID, you can get that value back out. And it doesn't matter how many times, how many functions you pass it through, where it's gone, you can still get that value out, unless it's been overwritten. But the crucial thing here is that contexts are immutable. So that's great because they're thread safe. You can pass them around. You don't have to worry about 10 trillion Go routines or touching the one shared piece of memory and everything exploding as a result. But that does have some disadvantages because as long as you're passing these things down a function graph that's really straightforward, that's really easy to understand. I ran some code a second ago. I now run some other code that is a descendant of this function. Therefore, my value is still there. If you have things such as middlewares where you're passing things kind of in and out of a server, that gets a lot more complicated because although it may happen after, it may not happen within the same scope. And because it's immutable, you may not have access to those things. So to go back through this, say that we had a function which takes a context as the first parameter. So this is a really common pattern. I think in the standard library that literally says that most Go code at Google takes a context as the first parameter. At Monzo, that is also true. Unless the function is literally doing nothing or it's entirely self-contained, we strongly recommend that people pass a context through. And if they do, we can add lots of extra cool functionality. So you get loads of stuff for free. And all you have to do is put a context as your first parameter. It's a bit annoying, but the cost kind of the benefit massively outweighs the cost. So in this case, we might have a function, and sometime later, we'll have another function call. So we're going to pass the context down into the next one, and so on, and so on, and so on. Which seems kind of tedious, to be honest. Why am I doing this? If I was in Java, I'd have thread-scoped variables and various other things. But if you were doing that, you again have a different problem. You have shared memory. you don't have an immutable thing. You have to coordinate access to those variables. Well, in this case, you can pass it in, you can access a variable, and you know it's basically safe. As I mentioned, contexts are immutable, which means if I change a value in the context here, that is only going to cascade further down. So if I do some function calls and I kind of think, ooh, here I have access to like a really good piece of information, I'll drop that in for something else. It's not going to propagate all the way back up. So that's fine if you're working on a relatively simple system. It's quite easy to understand. But sometimes, I personally have hit this on more than one occasion, you'll spend a couple of days working out, where is my data? Where has it gone? I cannot understand why it's not there. And yeah, it's literally just because of this. So as I mentioned, lots of functions in the standard library now take contexts, yay. So one of the example would be a HTTP request. So you can make a request like normal, or you can use a with context method, which is going to add a context that you have into that. And one of the methods you can use on this would be a deadline, for example. So if we have our function that has a context, and we maybe set a deadline into that context, pass it into our HTTP function, and that's going to make a call to some remote API. And we'll assume that all remote APIs are like really, really reliable, in which case, all good, everyone has a happy day, no problems at all. Of course, that's not the case. So in this case, we will see the HTTP client in the binary that you're running in will have that deadline, and when that deadline expires, if the request hasn't returned, it will return for you, and you'll get an error. So you'll get a context cancellation error that the deadline has exceeded. So this is cool because you can use a HTTP round tripper to set things like request timeouts and like connection timeouts with a dialer. But this allows you to say, hey, I want the whole chain of requests in my entire application to take no more than like 20 seconds. And you have different problems there where you need to keep, like, if you're running across many servers, you would need to keep the clocks in sync, which is obviously a hard problem. In our case, we use, so we run primarily on Amazon, and we're using, I can't remember, AWS's new like time API thing, which basically means all of our like workers have like a 1 millisecond skew or less. So it's not something if you're doing like really, really fine-grained deadlines, but if you're saying, hey, don't take more than 10 minutes, like, that's pretty cool. So yeah, to go all the way back, the context interface is a relatively small thing, but by allowing us to set deadlines, store values, and crucially check if something has finished, and if the deadline had been exceeded here, this would have closed the done channel. So now you can check if that thing has actually finished in many different places. You can, like, with that relatively small interface, build like a load of really interesting things. So how would that be useful in a bank? That still doesn't make really much sense. We could build like some basic applications. We can send some requests with deadlines, but like, how does that actually apply to us? So as I mentioned, I work at a bank. So how would you go about building a bank? Good question. No one really knows that. Obviously, day one, you're going to open your text editor. I think I was using Atom at this point. Anyway, VS Code now for the win. Or obviously, much better alternatives. And obviously, then you intensely panic. So in our case, getting a banking license takes a really long time. Who would have thought? We thought it'd take about a year. Obviously, it took about 2. We actually launched like 2 years ago now, which has been insane. So from that point, we've obviously wrote a lot of code. And our application has got relatively complex. So when we were starting off, we wanted to build a relatively simple app, use like modern kind of architectures based on things like Netflix and various other things. So we have a big question like, what's going to happen here? I'm going to run in the cloud. That actually wasn't allowed in 2015. Fun story. Thankfully, the FCA released their updated cloud guidance later on in 2015, which meant we could stay on Amazon. Otherwise, we would have had to like move everything to like literally physically hosted like colo stuff, which would have been crazy. Very different story, I imagine. So thankfully, all good for us. And we're going to build an application, which is inevitably going to get large over time. So if you're building like any large application, you're going to end up adding loads and loads and loads of features, and you need to like think about kind of the life cycle of those. At what point do you remove features, or do things get infinitely complex? And as your team grows, that will get a lot more complex. In our case, we knew we'd have to integrate with like a load of different payment systems. And these are things where like SOAP using XML is the pinnacle of technology. Seriously. So a couple of years ago, we built our own MasterCard processor, written in Go. In order to write that in Go, Rich had to add the ebcdict code pages because that's how some of those APIs work. They don't use ASCII or like things like that. We're talking like 7 bits for letters here. Anyway, for that reason, we chose not to build one massive application. We'd build lots of small ones, and they communicate through some means. But that has also spiraled rapidly out of control. So we now have like, think about 1,050, 1,060 services, which 99% of them are written in Go. I think we've got a few Java and Scala ones. They are primarily communicating via HTTP. And a number of other like queues and various other things. So in this model, we have a phone somewhere on the internet that needs to access our infrastructure. That's going to make a request, let's say, to here. And then something insane is going to happen. Because like, and this is like so simplified. The system is so complex now that like, no one person can understand how these things work. So it's very much about like constraining sections of your infrastructure with like known APIs, which allows us to build like reliable systems. So in this case, let's say this one is very unhappy. And it might only be one instance, or you might be running many for high availability or a variety of other reasons, or it might just be all of them, like game over. That API call is just never going to work at this point. And there's lots of strategies you could use here. We could like have fallbacks in this thing over here, but like ultimately this thing's dead, so like nothing downstream is going to work on this request. So how do we debug this? One of these calls might go through like 100, maybe more services. Some of them might have like asynchronous hops, so the like synchronous RPC call might work, but then there might be other bits that are broken. They're running across like hundreds and hundreds of different servers. So if I want to get like the log lines, yeah, it's going to be something like this. And this is if I went to like one server. I need to go and get like 2 log lines from like 500 different servers. And that's clearly impossible. I'm far too impatient for that. So instead, we need some way to correlate like our log lines here. So we use a really basic logging library. This is on our GitHub, which is just a wrapper around CLog if anyone's used it. But it kind of provides like a really basic logging interface, kind of the same as lots of things. You have like different log levels. You can get like error, debug, trace. But crucially, it takes a context. And this means that we can pass some kind of request object into our logging library, and then we can do interesting things off that. So if we had some function, we'd have a context, we do some things, and then something bad happens, we can log an error. Oh no. And at that point, that will head into our logging implementation. So slog is like effectively an interface, and behind that, we've just got like a really basic thing that will pull out certain things out of the context and add them as like additional parameters. So in this case, we'll end up with something like this. And the crucial part here is we have a trace ID. So this is like a unique request identifier that will be present on every log line from a single request into our infrastructure. So in that world, we'll have a massive blob of an API. In a very similar way, we've broken this apart into lots and lots of different services. So like each path basically is a different service. We can scale them independently. They have different availability and kind of reliability guarantees. If someone like ships some like really amazing new feature, if it's a new API, no one's using it. Like there's no customer impact whatsoever. So we can deploy these things really quickly. We can let people make really rapid changes because it's not going to affect like the main APIs. You can still freeze your card because that's a really simple API. It's very unlikely to break. You have lots of tests. And you can deploy something over here, so that it goes wild, and Kubernetes will constrain it. Not going to use all the CPU in your memory, and it's cool. So we can whiz away with that, but we've just made this problem even worse. We now have another hop here. And every one of these hops gets more complex because they're probably running on different servers. So in this case, we go into our like basic, what we call like an edge gateway or edge proxy. It's like an API gateway pattern. And at this point, this is like the very top. There's a HTTP server, like literally the Go HTTP server. When we, that will initiate a background context, and we can put a trace ID, generate a trace ID, and pop that in. So in our case, we'll just use a type 4 UID, and then we will store that in the request context. So our request, this I think is also open source. We have a Typhon library, which is just like a really basic, every request, like a service is just a thing that takes a request and returns a response. And the request satisfies the context interface, and it will store context in here. So we can generate a trace ID, we can store it with a known key, and then we can store that as an updated context, and we can pass that all the way down. So in this case, we'll now go to the separate API service, different server. When we log, we'll have a trace ID. We go off to some more maybe in parallel. Again, we have a trace ID. And to the point that you can even do this across asynchronous boundaries. So one of the tools I'll come on to later allows you to view these. But most of the common ones, like Zipkin or Jaeger, I think, they can trace like a synchronous call. But if you're passing a request ID, you can correlate those across like, hey, this went into a queue, and like 20 hours later, this queuing thing was caused by that request, which is kind of cool. So how do you go about doing that? So we have like 2 Go programs, and we have to somehow, we have a function, we generated a trace ID, we put it in the context, we called another function, pass the context in, pass the context in, pass the context in, all good. And then we hit the edge of our binary, which is a problem. So at this point, we have to do something to somehow marshal these things up, pass them over to the next one, unmarshal them, and then carry on. So we're using HTTP to send stuff between services. So we need to take specific things out of the context and put them as headers for our HTTP request. And then on the other end, on our server, we need to take specific headers out of the request, put them into the context, and pass them all the way down. So we can do that with, like, don't worry about reading all this code. But here, right at the top, we have some HTTP headers. So on the, where are we going to go? So yeah, we can look at we can pull the set of HTTP headers out of the context, and we can assert that it is a HTTP header, which you can iterate over. We can check if that's okay, and it's not nil. We can iterate over the headers and store those in the context. And then when we go out of the binary, when we come into the binary in a server, we again can get the headers, iterate over the headers, put them in the context, and then create a new context because the previous one was immutable with the headers in, and then pass that down our call graph. So in this case, we end up with HTTP that's going between these. When we're doing a HTTP request or serving things, we have like a number of functions, middlewares, whatever people call them these days. Filters, I think we call them. So in that case, again, they satisfy a very basic interface. They take the request and they give you a response, but you can chain them, so you can pass things through. And one of them will do this tracing thing both on the client and server. So this is something that like no one ever needs to think about ever again. It works, usually. Come on to that. And in the middle, although our services can pretend it's HTTP, we're sending that via Envoy, which is like a service mesh. So this will do nice things like retries. So if we send a request to one instance and it fails with like a 500, we might then try it against a different one. If it times out, it will have its own timeout there, so it will try another one. However, we'll just pretend that HTTP is magic in the middle. And yeah, again, like for most people who are building like services and business logic, you don't need to think about what's happening in the middle. Just like do a thing, the trace ID will be passed all the way through as long as you pass the context through, and magic happens. So in this world, we have an app that's kicked off something, which if we use a tracing tool, so we use Jaeger, we can aggregate all of these things up. They go off to like a centralized thing, and we can draw a call graph so we can see like how much time each thing's taken. Of course, this is a very simplified version. This is a slightly less complex one, slightly more complex one. And this is super useful because like, what the hell happened here? Like, all this stuff is like half a millisecond, like get a lock from etcd, release the lock, like 0.2 of a millisecond, something insane, do like millions of different HTTP calls. You can see like some of these things are happening like with offset times because they're happening concurrently. But yeah, like if we're investigating things, like that's where we start. So by understanding that, we can like know where to focus our time and effort. But that is heavily dependent on us passing like a really simple context around. Like that's the only thing. We put an ID in, that was it, passed it through, and you can build stuff like this. And actually, I mentioned like Envoy would do retries here. In that case, you actually see like a mini call graph just get repeated and repeated and repeated because it will try like a configurable number of times to redo the request. So the things that we're trying to do here are by passing a trace ID around, we can correlate the logs. We can observe things like database queries. So we pass this into through GoSQL into our database driver. That has access to the query string for Cassandra, so we can log that as a trace thing, and that will show up in the Jaeger graph. So I can click on a Cassandra thing, and I can see like literally select blob, and see why it took so long potentially. So yeah, we can do things like database queries. If we're publishing to Kafka or SQ, again, we can see which node it went to, which IP, why it took so long. And again, the same with distributed logs. We use those for, we use etcd for those. So the main things we're getting from this are that we can understand our request flow. We can understand what's slow, what's broken, and like understand kind of how like relatively complex systems work. So in this case, when this has happened, we end up with, like, as I mentioned, where this one's broken. One thing we might want to do here is if it breaks halfway through, it might have issued a number of requests that we now don't want to continue. So in this case, we, again, exactly the same thing. The context allows you to cancel a context, which will propagate to the descendants. So that will close the channel, and that will close the channel of all the descendant contexts and all the way down. So by passing a context through, you can just cancel the top one, and it will propagate all the way through. And the GoHTTP standard library will do that for you. So if you're running just a normal HTTP server, when the connection disconnects, like a client disconnect, it will close the context and propagate that the whole way down. So in HTTP 1, it will just terminate connection. And this works in the client as well, essentially same as a deadline being exceeded. And in HTTP 2, you don't need to terminate the TCP connection. It will like issue a request cancellation. So in this case, you'll end up with like the context cancelled in this descendant service. That will propagate further down. So you can cancel like outstanding work. And you can use that in really interesting ways. If you're worried about tail latencies, you could actually fire multiple ones, like multiple idempotent like GET requests at the same time. And then whenever the first one comes back, you just terminate the rest. And you'll always get like, you'll chop a whole load of like tail latencies off the end. Yeah, so that sounds awesome. Cancel outstanding work, yay. Decrease the tail latencies, everyone loves that. Reduce load on the database, great. Save lots of money, cool. Party time. And you can do that in like interesting ways. You can, like, if we dispatched a Go routine that will send a response on a channel, we can then select for like the response or when the context is done. So in the case of the context closing because something else has happened, we'll just return an error, like the thing didn't complete. And that context has been passed into the next request, so that will also propagate down. So this is like one mechanism. You can do it with a relatively small amount of code. So you can dispatch a request, return when you're done. But like an even simpler way would be you can do a default case. So if the channel is still open, we'll just pass straight through the default case and carry on going. So you can do this as like a kind of gate at the top of like a really expensive function. If you're doing something that was like very computationally expensive, but you weren't making other calls to databases and things, or like crossing function boundaries where you might check again, this will allow you to like stop at the top and like avoid that if you don't want to do any more work. So yeah, this allows you to just check if the context is done and abort if not. So this is cool. Again, save lots of money potentially, simplify things, make things faster, yay. Except maybe if you're a financial institution and sometimes you want those things to finish, and that is problematic. So in this case, my experience with this personally was we moved from using an elastic load balancer to an application load balancer on AWS a while back. We used lots of different ones, but like this one main one, we switched from an ELB to an ALB. And an ELB doesn't terminate a connection. If the person like gets bored because they're waiting for your thing to load, just close the app, nothing happens. Like the ELB keeps the connection open for like a minute or however long. It doesn't terminate it. An ALB, however, is like super helpful and just cuts the connection off, and as I mentioned, this will now propagate all the way through our infrastructure. So when we switched from an ELB to an ALB, we went from like, cool, no errors on our graphs, pretty happy with that, looking good. ALB, like everything's on fire. There's so many errors. We're like, is this even a problem? We're not sure. Roll back. How do we safely test this? Like, can we move a percentage of traffic over to this thing and like make it non-deterministic so someone would only get like one failed request? It was people closing their phones. Like, yeah. Client disconnects, got bored. Cascading errors, failure everywhere. Intense panic. Yeah, that was a fun couple of weeks. So in this case, yeah, we have a problem where we've been almost too good at propagating things and trying to save ourselves some work. And this model is great until that point. So there are some options. You could do this. This is like serious danger zone. So in this world, you have now separated those two things. And if that is like because you are going to run a cleanup operation, which could fail if the binary fails, but it has a reasonable chance of success, that might be okay. But if that's not the case, then this will now potentially never exit if the code below never exits. So yeah, you can do things like this, or you could reset a new deadline. Cancel functions are propagated either way, so that won't make any difference. Yeah. So the main thing that we get from contexts, even though they're like really simple, we can put request scope variables in. So that's useful if you're passing around like a trace ID. But even within a service, you can pass around things that are a bit more complicated. So you can use them for dependency injection, for good or ill. So you could initialize a logger, for example, that has particular configuration. You can put that into the context. And as long as you know the key and you take it back out, check if you actually got it, and then like type assert it's the right thing, you can use that all the way down. So if you've like configured something specific for that request, doing that, you could pass pointers around to that. However, at that point, you've gone from an entirely immutable structure to something that now is heavily mutable, and you'll need like to manage the coordination there. So the main way that we use this is to kind of store variables, deadlines, things like that. And usually the way we'll do that is by passing a variable into a package, which will have like a setter and a getter, so it knows the key, which I think I had back in one of the other examples. Yeah, so kind of doing that, and by having this like sweet purse we can carry around, by storing everything in there and it just being available to the right things allows us to build lots of code in the middle that like knows about banking and financial systems. But then passing request IDs all the way through means like we can build tools and use tools that you get for free. Like no one needs to go and think about passing trace IDs around everything. They just like write some code, pass a context through, and then go and look at graphs. And that is like a really nice thing for development. Yeah, and that's it. Hopefully I'm not too over time. I feel rude.